Now let us solve question number 4 of exercise 1.1 real numbers. According to the question, use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Now, if you remember, the question number 2 that we solved was very similar to this question, as we are given the equation in the form of 3m or 3m plus 1, where m is some integer, and what we need to do in that question, we were asked about the positive odd integers, whereas over here we are asked to solve the square of any positive integer. Okay, so the thing to be noticed is square of any positive integer. Now, moving forward, let me quickly write the same thing that we wrote it over there. Solution. Let A be any positive integer, and when we compare the Euclid's division lemma equation, we can see that instead of b they have given 3. So what is the value of b? B is equals to 3 according to the question. Now let us write the equation. The equation for as Euclid's division lemma, we know the equation as A is equals to BQ plus R, where R can be less than B but greater than or equal to 0, and hence we can write the possible values of B as well. So what are the possible values of B? R. R equals to 0, 1 or 2. A number less than 3 ranging from 0, because it can be less than or equal to 0. So now substituting all the values in the given equation, we will try to prove the given question. Okay, so when R is equals to 0, then what we need to do? We need to again putting the values, what we will get is A equals to 3Q plus 0. Instead of R, we are putting 0. So now, as the question says, it is the square, so we will squaring both sides. A square is equals to 3Q square, which will give us A square equals to 9Q to the power 2. This, as we have to bring it to this form, so what we will do, we will take the common as 3Q square, and we will consider 3Q square as K1. Let us just assume, so it is A square equals to 3K1. Now again doing the same thing and putting R equals to 1. We'll substitute the value 3q plus 1. Now squaring both sides, 3q plus 1 whole square. This is in the form of a plus b whole square. So we'll put the formula and expand it. A square equals to, the formula is a square plus 2ab plus b square. So this will result in 9q square plus 2ab, that is 6q plus 1 square is 1. Now we'll take common from these two numbers. A square equals to 3q square plus 2q plus 1. Now again we'll consider this value as k2. Putting the values, a square equals to 3k2 plus 1. Now again we will solve for r equals to 2. Again writing the equation 3q plus 2, squaring both sides, 3q plus 2 whole power 2. This will result in 9q square plus 12q plus 4. Now observe very nicely that we can write this equation as also in this form. A square equals to 9q square plus 12q plus 3 plus 1. Okay, 3 plus 1 is nothing but what? 4. So now again taking common, a square equals to 3q square plus 4q plus 1 plus 1, and this is nothing but a square is equal to 3. I am considering this as k3, so k3 plus 1. Clear up to this point? So in this way we can write that where k1, k2 and k3 is nothing but some integer, and in the given question m is also some integer. So we can also write it down like k1, k2, k3 is what? Is some integer. And according to the question, m is also some integer. So we can also write it as 3m for this one, or 3m plus 1 for this one, and the same 3m plus 1 for this as well. And hence we proved that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer.